Good morning, good afternoon, good evening, mammals. I'm not going to tag this with an NTI number just because at this point it's getting meaningless. Instead, I'm going to tell you where it fits in our sequence. I'm posting this on April the 1st. Happy April Fool's Days. In the course sequence, it goes after the video on orbital notation, and it's our second video in our last unit, which is the advanced bonding catch-all unit. And I'm going to be talking about two concepts, shielding and effective nuclear charge, that are going to be our source for any kind of explanation for the properties that we're going to be talking about later. So if you have to write any question comparing properties such as ionization energy, electron affinity, atomic radius, electronegativity, you need to refer to the concepts of shielding and effective nuclear charge in your answer. And when I cover those properties in specific detail, I'll be explaining their differences and why they increase or decrease as they do using these concepts. So it's our starting point. To help think about effective nuclear charge and shielding, I'm going to use these Bohr models, which have some terrible assumptions within them, but they're useful, and I'll talk about those assumptions and where they break down as we come to them. The key things to note is I've taken the electron configuration and I've put all of the electrons on their respective shells with increasing distance from the nucleus, and inside the nucleus I've also labeled the number of protons. The electrons we're going to conceptually divide into two camps. The valence electrons, they're the ones that go on the outside. They're the ones that we usually care about for determining any particular property, because since they're on the outside, any changes to the atom, they're going to be the ones that experience that change first. And then all of the other electrons, the inner electrons, because they are between the valence shell and the inner shell. And as I mentioned, the protons are also labeled because we're going to be thinking about the attractive force between electrons and protons because they have opposite charges. And we're also going to be considering the repulsive force that an electron feels from other electrons. And that's what we call shielding. So this shielding is our repulsive force, because electrons all have the same charge and they repel each other. For our purposes, we're going to say that the valence electrons don't shield each other, because since they're all on the outside, they aren't really in between the other valence electrons and the nucleus. The electrons that create shielding are the inners, because they're in between the valence electrons and what they're attracted to, the nucleus. So we're thinking about a positive attractive force towards the nucleus and a repulsive force from the inner electrons on the way back out. That is kind of our assumption. You know, valence electrons, they also repel each other. They just aren't situated in the atom in a way to very effectively repel each other. And our other assumption is that we're treating all inner electrons the same and creating the same amount of shielding, because we're thinking about them being on these concentric rings. If you go back to the orbital notation video, the shapes of the orbitals aren't concentric rings, so that's going to cause a problem for us and create some exceptions to these patterns, and we'll deal with that when we come to it specifically. But just saying for right now, that's the limitation of this model, is that we're pretending that the valence electrons basically have no shielding, and we're treating all inners as equivalently repulsive. What that leaves us with is a net charge. Between the attraction that electrons feel for the nucleus and the repulsion that they feel from other electrons. An effective nuclear charge is just boiling down all of the repulsions from all of the different electrons and all of the attractions from all of the protons present into kind of one number, one net force that we can use to compare things against. And we're going to think about how this changes both horizontally and vertically on the periodic table. Let me say up front, I want to give you a way of thinking about this that may not be safe to write about on the test. And then I'll give you kind of the test safe answer to talk about it. And it comes down to the breakdown in some of those assumptions. I want to consider horizontal first. And I've got two atoms here that are in the same row on the periodic table, germanium and bromine. I want to look at first what is the same for them. They have the same number of inner electrons. So they have the same amount of shielding or repulsive force because they have the same inner electrons. They do have a different total number of electrons because as we go right on the periodic table, we do add electrons to it, but they're being added to the valence shell, and we disregard the valence electrons by pretending that they don't create any shielding. What is also different is the neutrons, and we don't need to consider that since neutrons being neutral don't interact with electrons. And their protons are different. And that matters because as we go to the right and add more protons, we have a higher nuclear charge, a more attractive nucleus. So the net force is going to increase as we go right because we're keeping the same repulsive force but adding a greater attractive force. So if I kind of made this sort of like free body diagram style, I would have a bigger attractive force for bromine with equivalent repulsive forces. So bromine would have a higher effective nuclear charge. Effective nuclear charge is increasing as we go right. The not safe way of thinking about this, if you're kind of mathematical, is to consider the ratio of protons to inner shell electrons, and you can see that that increases as we go to the right. But that's not AP safe language because of the breakdown that the inner electrons are not truly creating equivalent amounts of shielding. Your AP safe language is to say that the attractive force increases as you add protons, but you have the same amount of shielding. Don't talk about the difference in valence electrons or saying that they don't contribute to shielding because that's not true. They do, they just don't contribute very much. Stick to comparing the number of protons while saying that the number of inner shells stays the same. Going to do the same thing for a vertical trend, kind of explain it in a way that might help you think about it and understand it, but isn't test safe and leave you with the way to write about this on the test. Let's consider what's the same. Valence electrons are the same, but that does not matter because we're pretending that they don't contribute to shielding. What's different? Neutrons, doesn't matter. Inner electrons are different. So as we go down, we create more shielding, more repulsive force. Protons are different. As we go down, we're also increasing protons, so more nuclear charge. It really does not want me to finish that E deal. And this presents a confounding factor because I have an increasing repulsive force and an increasing attractive force. And how do you know which one of those wins out? For the situations that the AP test is going to ask you about, the repulsive force is going to win out. It's not always true, but in the situations where you're going to be asked to justify it, it's going to be true. Again, I'm going to show you in a not AP safe way, but to try and convince you of this, because the inner electrons increased by 18 and the protons increased by 18. So in absolute terms, they both went up by the same amount, but in relative terms, 18 to 46 is a larger increase proportionally than 32 to 50. So the repulsive force has increased relatively more compared to the attractive force. This is not universally the same, and when we look at some trends in particular, we'll see where that breaks down. But for the AP test, that's going to be your case. So that means for your safe answer, AP safe answer, and we're not going to write about this, you're just going to say as you go down, effective nuclear charge decreases because there are more inner shells creating shielding. Don't talk about the attractive force increasing. Don't talk about the shielding increasing more relative to the attractive force, because that's not safe as a blanket statement. If asked about a vertical change, stick to this. To summarize, I want to sketch a quick periodic table, because anytime that I'm asked to think about a horizontal and a vertical trend, I sort of turn them into a diagonal and think about corners. So effective nuclear charge increases as we go to the right and increases as we go up. So I like to think about this diagonal. Where helium is going to have the largest effective nuclear charge, its electrons feel the most attractive force for its nucleus, and francium has the lowest effective nuclear charge. Its electrons feel the weakest amount of attraction for the nucleus. What I'll ask on today's assignment, as far as following up on these notes, is that you just explain why effective nuclear charge increases as you go to the right and decreases as you go down in AP safe language. So don't give me any of that ratio stuff that I was talking about. Stick to nuclear charge, more protons, increases as you go to the right with the same amount of shielding. As you go down, you just say that the number of inner shells increases, creating more shielding. Effective nuclear charge decreases. I'll leave it there for today. As always, take care of yourself and others, and I'll see you on the flip side.